do you mean leaving group? Something left. Okay, I agree. Something left. What was that something? So this whole piece.
Yeah.
Okay, is that it?
Hydrogen added
Where was the hydrogen added?
on the carbon where that ester group left.
We end up attaching one more hydrogen there. Okay, it's kind of crazy. What's the charge on the hydrogen most likely to be? Why are you saying a positive hydrogen and not a negative hydrogen? Okay. Notice that we're adding H3O plus, so we've got an H plus source, so very likely it's going to be a positive hydrogen. Okay, if it's going to be a positive hydrogen, that's an H plus, what charge was the carbon? Carbon had to have been negative. Okay. If we just kind of step backwards from that, just pop the hydrogen off. Was that a stable negative carbon? We erase that hydrogen, put a negative charge there. Is that negative allowed to form? Would that be stable?
Yes, resonance.
Yes, resonance. Resonance with what known structure?
Asking for functional group,
Yep.
carbonyl.
Is resonating with the carbonyl to produce what known structure? The enolate. Yay. Okay, enolates coming back to haunt us. Still need to know them. Okay. So I can form that negative carbon because it is resonance stabilized. So cool, I could explain now, theoretically, the last part of this, placing the hydrogen onto the structure. How the hell do I explain the rest of this? If that carbon was negative, what does that mean the carbon in that giant leaving group needs to be? What? It needs to be positive. Well, is that a leap to say that that carbon is positive? Why not? Why is it positive? We have electronegative oxygens drawing electron density away. So we can see all of our charge density stabilizing out and working for us in some respect. Okay? So let's try to kind of backtrack through some pieces here. So we are suggesting that somehow or another we can generate this species and we can generate this species. Right? Okay. Is that a particularly stable species? Not really. We got a positive carbon. We're missing an octet. We could do resonance. We've got lone pairs on our oxygens that could potentially donate in to stabilize that. Okay. But it would still be a formally positive structure, which would very likely react with the negative carbon. So we got the right idea at least, but whatever that red thing is needs to be incredibly stable to facilitate this reaction. And as shown, all we're really doing is resonance. It's still going to be positively charged. So somehow or another, I need that red thing to become stable. Kind of make sense? Okay. So let's kind of work our way through. So we've got an idea on what's happening with our pieces. We've got an idea on how things need to kind of shatter apart from each other. If we were to add curved arrows, something needs to happen where those electrons go out to our carbon. Okay? Something would then need to stabilize that positive carbon. What would be a good thing to stabilize that positive carbon? Just in general. Electrons. Are there electrons nearby?
Oxygen.
Yeah, we do have electrons from our oxygens that could potentially be used to stabilize that. But again, we're really only generating resonance, and that's not the greatest thing on the planet. Okay? So maybe we've got to address something else happening first. Okay? So we've got our idea. We need to come up with pieces that allow us to propagate there. Okay, so now that we've got our basic ideas, let's see what we can do with our reagents. Okay. What reagent are we given? The only one you can name. H3O+. Okay. How is that reactive? It's an acid. It's going to give up H+. So what do we need to stabilize that H+? A minus. Well, we're in an acidic environment. Are we going to find a minus? No. So I don't accept a minus. What do we need to find? Yes, we need to find electrons. Where do we have electrons in our structure? Okay. We have lone pairs on our oxygens that could all potentially react. Okay. Which ones? Or which one of those oxygens?
Stable one?
Ah, the least stable one. Okay. Said another way, the most...
Reactive.
Fair enough. Reactive. Get more specific.
The most worst. Best worst.
What did H3O plus act as?
Yes. That's base.
What do we need to be finding in our structure? The most basic, oxygen. Okay. So, what do we got? You should. Go ahead.
We can get a negative oxygen on the right from the carbonyl.
Can we get a negative oxygen?
Oh, we can, but we can get a positive oxygen through resonance. So I'm saying the most basic is the top right.
Okay. So we're getting a call that that one, our red one, is now our most basic. And then we have what we'll call our purple one and what we'll call our black one, which I drew over in black. That was kind of dumb, but whatever. What do we think? Why would the red one be the most basic? What are you suggesting?
You can get resonance from the ester, or the oxygen that's in between the two. Yeah, that way.
The purple oxygen donates electrons in. What does that mean about its basicity? What does it need to do to act as a base? It needs to give up its electrons to hydrogen. If those electrons are going into the structure, can they go to hydrogen? Which means not basic. Our purple one's not a good base. It's involved in resonance within the structure. That is not going to be a good base. Okay? But if it shares those electrons inwards, what happens to now my red carbon, my red dotted carbon?
Exceeds the octet.
Exceeds the octet. What do we do when we exceed the octet?
Get rid of electrons.
We have to break a bond. We have to get rid of electrons somehow. Do we have an easy to break bond? Yeah, we have that polar pi bond. Those electrons can shuttle up to that oxygen. Okay, making that oxygen negatively charged. What are we trying to find for a base? Negative charge. Hey, that's not too bad. We got some electrons up there. What about our black oxygen? couldn't I have said that I just take those pi electrons and put them on the oxygen? Don't I generate a negative charge there too?
Break octet.
There's no octet breaking there.
The carbon.
Sorry, you under octet. Yeah, I see where you're going with break octet. Okay, so we'd have that positive charge on that carbon, so that's a bad resonance structure. Whereas our red oxygen has a good resonance structure, generating our negative charge. The black one has a bad resonance structure, generating a negative charge. Which one's more basic?
The one that gets the negative charge.
The one that actually builds the negative charge. Okay? So by using our understanding of charge, size, electronegativity, resonance, okay, inductive effects, and the definitions of acids and bases, we can determine that the red oxygen is our most basic. Okay? How else do we do it? You memorize this. You got a lot to memorize. I don't recommend that. So let's go back. So we said the red oxygen is the one that's going to be the most basic. Okay? We dealt with the resonance and all that to help us determine the red oxygen was the reactive one, but I do not need to show that in a mechanism. All I need to show is the red oxygen shares electrons with my H3O+, also written as H2O+. What do we get? Anybody challenge that?
Positive oxygen.
The oxygen is positively charged. Did I react the pi bond? No, I took the lone pairs.
Oh, you did it through okay.
But you're bringing up an interesting question.
You were just proving that that was the most basic oxygen by resonance.
All that resonance I showed, yes, was to prove that was the most basic. Okay? But the reason it's more basic is because this structure is stable. Why is this structure stabilized?
You have the difference between a positive oxygen and a positive oxygen.
I have a variety of forms of resonance. And for those of you in the lab, this becomes relevant because you were asked to draw a mechanism. And in a mechanism, what do you need to specify? You need to show all the resonance contributors that allow you to understand why that reaction occurred. Okay? And since I'm making you do it in the lab, and because I have a stupidly large amount of time to go through and show all this, we'll go ahead and show it all. Okay? So, is that structure stable? Or did anybody have any questions about it? I was looking at it and being like, cool, yeah. You didn't screw up yet, Mike. Keep going. I'm going to take silence to mean I didn't screw up yet. No, dang it. What are you saying, Tyler?
I'm just kind of curious. Is that an enolate, or is that a?
That is not an enolate because we have an oxygen there. We don't have an ene of our 8, so we can't do an enolate. Okay. So where we are currently at, this is the bottom kind of middle, and I'm going to be going up from there. Is that structure stable? Yeah, you look at that and you're like, yep, that structure totally stable.
It has a lot of resonance to stabilize it.
It has resonance to stabilize it. Do we need to be concerned about it being stable?
It has a positive charge.
It has a positive charge. Is that positive charge on an atom that's happy with a positive charge? No. So is it stable? No. So what needs to happen?
Needs more electrons.
It needs electrons. So what does that oxygen do?
Takes the electron.
Takes the electrons. Which electrons does it take?
The pi bond.
Why do we go from the pi bond and not either of the sigma bonds?
Because it's higher in energy.
The pi bond is higher in energy than our sigma bonds. Okay, what is the problem with removing those electrons?
Carbon becomes positive.
The carbon would become positive, and that would take us backwards. Okay? So we still need to focus on moving forwards from this structure. So we need something to come in there and stabilize that positive carbon. What do we need to stabilize the positive carbon? Electrons. We just showed a bunch of resonance with oxygens and the electrons within the structure. And that's great. That shows that that is a valid maneuver to do with our very first step. Okay? But it does generate a higher energy species. We need to stabilize that somehow. We need electrons from somewhere else. Where else do we have electrons? Water is floating around in solution. Water can come in and attack. What do we end up making? What's that? I won't quite accept hydrate. Tetrahedral intermediate is more correct. We do have a pseudo hydrate. It's a little bit weird because we have that O R group there. And in all honesty, I don't know that you could call that a hydrate. You've added water, so technically, yeah, but I wouldn't call that a hydrate.
Like add water across?
Yeah. So, is that structure stable? What's unstable about it? Positive oxygen. Oh, that's interesting. I wonder if we're seeing a pattern show up here. How does that oxygen get stabilized? Hydrogen leaves. Okay, we've been saying this a lot, and I've been yelling at you a lot about it. Hydrogen leaves. Oxygen takes electrons from the hydrogen. Hydrogen does not leave. By saying leave, we are saying it takes the electrons with it. Hydrogen will never take electrons away from oxygen because electronegativity. Hydrogen is removed from the structure by something remotely basic. And for those of you trying to think or thinking that we don't have very many steps left to go, I'm going to run out of space very, very quickly here. Still reactive, not reactive?
There's still a carbon, but there's no charge.
No more charge. Okay, but we have 3 very electronegative atoms attached to a carbon. Okay, and remember what we talked about with our carbon. This is one of the reasons why the hydrates were so unstable, and we reverted back to the carbonyl. If we have the opportunity to have a carbonyl, we must take it. Is it possible to form a carbonyl? To form a carbonyl, what do we need? We need a carbon, and we need an oxygen, and we need a pi bond between them. To form that pi bond, what do I need? Electrons. Okay. Do my oxygens have electrons? Yes. Okay. Which one should I use? They're the same? Red, purple, and black are all the same. Red and black are the same. Okay, so really all we're caring about here actually is red versus purple. Which of those would be more likely to share electrons? Why?
Hydrogen's less electronegative than the carbon attached to it.
Hydrogen is slightly less electronegative than the carbon attached to our oxygen, meaning the carbon could potentially withdraw electrons from that oxygen, from our purple oxygen, making it less likely to share electrons. The red one is more likely to share in. So it shares in. What's the problem with that? We break the octet, so what do we have to do? We need to kick out a leaving group. Where's our leaving group? Black or purple? Why purple? Why not black? We just added black. What's stupid? Let's not kick it back out. That just takes us backwards. Okay, so let's do something different. Why not? Let's see if that takes us someplace. What do we get?
Would it be able to hold the negative charge better because it's connected to that carbon? So it's stabilizing the negative charge.
There's an interesting question. Everybody agree? Anybody have a problem with those products? We have a negative. Why is that a problem? We're in an acidic environment. Was that step valid? Nope. Sorry. Erase. Okay. We absolutely need that oxygen to share electrons downwards. So we have the right idea behind it, but our mechanism is invalid. Okay, which kind of sucks, but we have to work through it. How can we make sure that we never form that negative charge? What if we have an acid? Oh crap, we're in H3O+. Yes, we have acid still floating around in solution. What should we do? Protonate our leaving group first. Does oxygen want to be positively charged? What does it do? It can take the electrons and leave the structure. Okay. Giving us a carbocation. Are carbocations good to form? Not really. So generally a good idea to make sure that we don't actually see that form at least immediately. Okay. And this is where we're going to start erasing. Am I good to start erasing like 2 or 3 steps back? It's going to be fun if somebody just skips to the end of this, try and figure out the mechanism. They're going to be like, what the hell? Okay. Looking at that structure, is it stable? What's wrong with it? Positive on the oxygen, what do we need to do? Steal the electrons from hydrogen. What do we end up with? Don't all shout it out at once. What do we have? Carboxylic acid. Great. Fantastic. Phenomenal. We changed the structure, but our whole goal was to do what? Get rid of that whole piece. Well, did I do something productive? Yeah, I got rid of some of it. I just didn't get rid of all of it. Okay. Okay, so now we've got a new question. Because really what I'm looking at, we go all the way back to the beginning now, is I'm starting with that structure. Okay, so is everybody good with everything that's up there? Can I erase everything? 3, 2, 1, you're going to kill me, but, or kill me when you say no, wait. But anyway. So really now what we're looking at is this question. Again, what needs to happen? Let's summarize, because now we've started to progress closer to where we want. Okay, but we aren't there yet, so we still want to identify the things that are changing. What are the things that need to change? I still need to lose this piece. What else do I need to do? Still need to add that hydrogen. What charge is that hydrogen likely being added as? A positive. If it's still coming on as a positive, what charge was the carbon? Still likely a negative, which then means when we go back to our starting material, we're still likely a negative here, and we still need to have likely a positive. Oh no, that's the good color on that carbon. Okay, so let's just split that. Break it off. Why not? Let's just see what happens. What if we were somehow able to do that? All right, Same thing that we did before. And the last time we said, well, yeah, there were electrons to stabilize, but all we end up doing is going around in circles with the resonance structures. How about this time? Anything change? Same thing, we just go around in circles? Yeah, dang it. Yeah, you're right. We just keep going around in circles with resonance. And we notice anything potentially interesting about either of those structures?
CO2.
That looks an awful lot like carbon dioxide. What do we know about carbon dioxide? It's a gas. Okay, which means it would leave solution. Well, if it's left solution, could we do the reverse? Ooh, that's useful. What else do we know about carbon dioxide? It's always fun to bring in some environmental chemistry into this. Safe. Kinda.
If you're a plant.
You're a plant, that's a little bit better. Okay, if we just breathed carbon dioxide, we'd have a problem. It's good for the environment, right? Okay. We just dump tons of CO2 into our atmosphere, no problems whatsoever.
The next part, you should probably know.
What's that?
Just comment.
What happens when we dump tons of CO2 into our atmosphere?
You get global warming.
Wait, you get what? You get global warming. So CO2 is a bit of a problem, okay? But it's not that big of a problem because we as humans have solved how to get rid of CO2 from the atmosphere, because that was really easy. We just take it and we just put it into plants, and that just goes really fast, right?
Keep killing plants.
Oh no, we haven't solved that problem. I wonder why. What is a characteristic of CO2?
It's a gas.
Yeah, it's a gas.
It's hard to get. No.
Not quite where we need to go with that.
It absorbs heat.
Why have we not just pulled it out of the atmosphere?
Oh, because it's stable.
CO2 is stupidly stable, which makes it insanely difficult to turn CO2 into anything useful, even for organic chemistry. Once we form CO2, not only does it bubble out of the reaction, but it is now such an incredibly stable molecule that it's not going to react. How do we get CO2 to react? We have to generate a carbon nucleophile. Oh, those were really easy. Oh, wait, no, they weren't. That's why we had all of our carbon nucleophile reactions picked up the name of the person who discovered it. Okay? CO2 is an incredibly stable molecule. This is one of the reasons why there's tons of active research in how we can trap and contain CO2 and convert it into something useful, like ethanol, because ethanol can be used to drink and forget about all our worries, as a fuel source to generate our cars, okay, or to start generating power. Okay? Then we've got a cyclic system. We generate CO2, but then we take that CO2 back down to ethanol, and we spit it back out as CO2. Okay? It's a closed loop. Whereas the current system, what do we have? We have an open loop. Okay? We allow plants billions of years to trap all of that carbon source. Then we burn it all and expect the plants in tens of years to do the exact same thing they did in billions of years with less of a population because we're cutting all the forest down. Yeah, that becomes kind of a problem. Okay. So there's my little stop off the
I
soapbox.
think the science is still out on all that.
Yeah, definitely. So,
Sorry, I'm cynical right now.
I don't blame you. So let's go back to our situation. We need CO2 to come off of this. What do we need for CO2? What has to happen to the CO2? How do I get CO2 from that structure? What happens if I get rid of the hydrogen? Well, where would the electrons go between the oxygen and the hydrogen? Why to the oxygen? It's more electronegative than the hydrogen. So we would expect our arrow to start this direction. what else would we, or where else would we expect those electrons to potentially go? Should they even stop at the oxygen? They could go all the way through. Come on, pen, do what I ask. To form a pi bond. What's the issue with that pi bond? We exceed the octet on our purple carbon. How do we fix that? We take the electrons and we give it to our other carbon. Okay. So there's an interesting question. Does it want to do all of this? Okay. So let's go through and I erased too much. Let's go through and piece that together. Okay. We shuttle there, we shuttle there. What do we get? There's our squiggle. There's our R group. We have those extra electrons.
That creates negative
To finish this, we need H+, and you're right, we'd have a negative carbon, and we can't have a negative carbon in solution. So, this gets us our CO2, but it makes the negative carbon. We can't have a negative carbon. Okay. Well, what if instead of forming a negative carbon, I took those electrons and I put them over there? What would my result then be?
Exceed the octet of that carbon.
I exceed the octet of the next carbon. Do I have a pi bond? Then I could put the electrons up onto the oxygen. Okay, cool. So I do all that. What do I end up with? Double bond, negative oxygen. Cool. Everything's happy except what did we just say we couldn't form? Negative oxygen. Rats. Okay. Still a problem. Oops. What changed? I did a rotation about that now blue sigma bond. Am I allowed to do that? Yeah. Okay. So let's go back through, summarize. We needed the electrons from that bond to come down to make our CO2. But then we needed the blue bond electrons come over here. But then the electrons from our pi bond would go up to the oxygen, but then the oxygen would be negatively charged. So I can't form a negative charge. Is there something positive nearby that could pick up that negative charge? Sure enough, there's a hydrogen right there. Now what happens? I've picked up my hydrogen. I have my oxygen that formed now a double bond to my carbon that has a double bond to another oxygen. The former bond there is broken. I have my CO2 and no negatively charged species. Not the enolate, but the enol. Okay? Why do we theorize that we get this happening? We know the end result happens, but it's still coming down to why do we say it happens this way? Why don't we just protonate the carbonyl? We could have done that. Okay? But the odds of that comes in becomes questionable, and we're just trying to come up with some other way or some way to put the hydrogen onto that carbonyl that we know needs to be there because we shouldn't be forming a negative charge because that's what makes sense within a reaction. Now the question becomes, where do we get that hydrogen from? We could have gotten it from the acid that we added to the solution, or we could get it from the acid that's shown here. Okay. This type of reaction is what type of reaction? I'll accept cyclic, yes. Keep going. It's a little bit weird to call it cyclic because do we end up with a cyclic product? No.
Coordination.
So what are you getting at when you're saying cyclic? Our reaction is happening internally, known as a intramolecular reaction. And what did we say about intramolecular reactions? They are not very likely to form. And yet, what are we showing here? An intramolecular reaction that should never form. When did we say intramolecular reactions are allowed to form? When they generate stable products. Stable products being 5 or 6-membered rings. Take a look at the transition for this reaction. What do we have? A 6-membered ring transition state. That is why the intramolecular reaction, or the intramolecular hydrogen elimination reaction is allowed to happen. Okay? That is why this is an acceptable mechanism. Okay? So lots of little pieces in putting it together and saying why we should do this. Okay? Students tend to have a hard time with it, probably because of looking at the charges, and probably because you don't remember that sigma bonds can rotate so that the hydrogen isn't close to that negatively charged oxygen when we initially draw it. It looks stupidly far away. But a simple bond rotation, and now everything lines up, everything works beautifully. Okay? So we now have our final correct answer, right? Oh, okay. What was wrong with it? Hydrogen's in the wrong place. So, okay, there it goes. How do I fix that?
Is that oxygen positively charged?
Oh, no, I did have it right the first time. For some reason, I saw the hydrogen and thought it had to be positively charged. That's my bad. So it needs to tautomerize. How does it tautomerize? Can I erase the CO2? How do we do the tautomerization? I heard somebody say it picks up what? Hydrogen. What picks up a hydrogen? Okay. Does that carbon have electrons to pick up? Okay, so we could take the pi bond. What would the result be? Are we allowed to form tertiary carbocations? Whoops. Okay, we have a stable-ish carbocation. Okay. That said, if we tried to enter that into our online homework, they would tell us we're wrong. Why are we wrong? What is the problem with a tertiary carbocation? Is a bad Lewis structure. So we want to alter our mechanism, okay, and I like your idea of the hydrogen getting picked up, but I need to alter it in such a way that I don't immediately jump to a bad Lewis structure. What electrons? Let's take the electrons from our oxygen and share those at the exact same instant. The result is I form the oxycarbon or the oxycation. Okay. Is that cation allowed to form? For it to be allowed to form, what should we see? Resonance. Do we have resonance? Whoops. I don't know why I drew the exact same structure again. We do have resonance of those electrons going back up. It is that resonance structure that allows us to say that we can form the oxycation. Do we end up showing the exact same structure that we had problems with before? Yes, but it's a question of when does it show up in our mechanism. Does it show up as an explanation for why we're allowed to do something, or does it show up as a valid intermediate? In the case of it being an explanation, it's valid. In the case of it being an intermediate, that's bad. Right? So it's getting into the nuances of identifying a mechanism. Is that our final answer?
No.
Either of those structures. What needs to happen?
Deprotonate the oxygen.
I need to deprotonate the oxygen. Okay. The tendency is to say, let's do this. Okay. Everybody see where I drew that arrow? Okay. Let me draw it again. I'll draw it in blue. Do something like this. Everybody see it now? Okay. Do you know what I mean by drawing that?
The hydrogen gets taken by something else.
It's okay. And where do the electrons go?
The oxygen.
Okay. Is that happening at the same time or a different time that the red arrow is happening? Different time. Okay. If I remove all the colors and we removed my vocalizations over the top of that, would you know that that meant a different time? No. Okay. Which is why we should not be showing it there. Where we should be showing it is with our other resonance structure. And you may say, well, but I can't do that. I don't see any reason why the oxygen would take the electrons from hydrogen.
Because it goes negative.
Because that would then go negative. So that's a bad idea. Maybe you shouldn't stop it going to the oxygen. You should take those electrons and go to our pi bond. We can move to our final product from any one of our structures for resonance. Why? Because our resonance structures are identical by definition. That is why they are resonance. Okay? It just means we might have to use extra arrows. That's okay.
Could you not go to the oxygen, make it negative, and then...
True. We could ignore the resonance structure. Okay. A lot of that comes down to what you are trying to do. Okay? On a multiple choice exam, what are you trying to do? Get the right answer. So how many times do you have to show a mechanism? Never. So do we need to show resonance for a mechanism to explain why a reaction worked on a multiple choice exam? No. When do we need to show the resonance? When you are drawing out a mechanism in a short answer question. Okay? When do we ask those questions? On the next exam, not on the final. Okay? Everybody get it? I think that's a really neat reaction, personally. That could be a subtle hint. It's kind of long, though. Okay? Could go through and take a look at what the textbook went through and showed. They showed some of the steps, not all of them. They focused really primarily on that bond rotation and doing the critical step of kicking out the CO2 to form the enol. And then they're just saying, yeah, you remember you did that tautomerization stuff? Go look at that. Okay. We walked through it all the way beginning to end. Okay. Questions about any of that? Okay. We can do the same thing kind of with our Osito acetic acid. The only thing that's different about it in comparison to the malonic acid or the malonic ester is that we are not dealing with a diester. Okay. The diester, so if we had the red O-ethyl out there, we then have our malonic. Okay. If we just get rid of that and it's no longer a diester, we just make it a carbonyl, okay, a ketone. This is now known as your acetoacetic acid or acetoacetic ester synthesis. This becomes nice because we can lengthen our carbon chain by how many carbons? Okay, and that's then going to come to a frame of reference. We can lengthen our red carbon chain by how many carbons? There's our red carbon chain. How many more carbons do we have? 3. Okay. We can chain lengthen with 3 carbons. Okay. So it's nice because we can then extend our structure theoretically with a limited amount of carbons. Potentially we could even go more than that if we had more carbons out there. If I added an extra carbon, would this be the acetoacetic ester synthesis? Why not? What was the acetic? What was the aceto? If I add an extra carbon, is it an aceto anymore? No. Okay. So it would technically change its name. Does it change the chemistry? No. The chemistry still stays the same. Kind of makes sense? Okay. The malonic ester. You're now looking at another reaction. What's special about the malonic ester? How many carbons are we adding? We're adding 2, and this time our functional group ends up becoming a carboxylic acid instead of a ketone. Okay. Why do we care? Well, it depends what you're trying to get to. If you want to make a carboxylic acid, you probably want to use the malonic ester. Okay. If you wanted a ketone, then you probably want to use the acetoacetic. Kind of makes sense? Your textbook has this big section on protecting carboxylic acids and amines, okay, within this section. Okay. What did we say about protecting groups before? Not what? Not green chemistry. Why? You're adding more steps. We're adding the step to put the protecting group on, and then we're adding the step to take it off. Okay. So to run 1 reaction step, I now have to run 3. Okay. That, regardless of yield at each of those steps, is going to drop my yield, period. The more steps we do, the lower our yield. Okay. Not only that, if we look at our overall molecular efficiency, I'm doing 3 times the work to do one thing, which would mean 3 times the waste. That is not something that we would want happening in green chemistry, so we try to avoid it as much as possible. Will we always avoid it? No. There are a lot of cases where sometimes it pops up. That's why it's showing up as a synthetic tool. Okay? So your textbook lists a bunch of those possible protecting groups. I won't test on them, and I'm pretty sure your textbook doesn't test on them either. Okay? At least as protecting groups. Okay? Realize that a lot of those show up as reactions you are being tested on. What's happening in that first one? You're going through a tetrahedral intermediate. It's the conversion between carboxylic acid and an ester. Are you being tested on that? Yes. Are you tested on the reverse of that? Yes. Okay. Are you being tested that that is a protecting group? Not really. Okay. So you are responsible for the chemistry happening within each of these. Okay. Recognizing that they're necessarily protecting groups and that you can reverse those, much less so. Okay. I think there might have been questions in the smart work. Is that even true? That may not even be true.
There was protected questions last week.
For the last unit, yes, I know that for sure, but I don't think I had any for this one. Yeah. So, not a big deal. I just want you to be aware of it. We can protect those functional groups. Yeah, we can protect those. After that, okay, we've got a big section in your textbook that brings in a whole bunch of stuff about protein synthesis, okay, which is really optional material. It's a bunch of named reactions, because when we look at biochemistry, how do biochemists come up with names? By whatever their mother gave them at birth. Okay? That's pretty much nomenclature system within biochemistry. Okay? You find a reaction, oh, I'm going to name it after me. Okay, why? Fucking biochemistry, stupid. It's not exactly true, but it's close enough. Okay? So, prideful. Okay? It is a relatively new field as far as chemistry goes, the biochemistry section of it, largely because what did we need to do to be able to do biochemistry? Organic chemistry. And since we didn't have a really good grasp of organic chemistry until the last 50 years, biochemistry really couldn't do anything useful. Okay? So when you get a biochemist saying, oh, there's no organic chemistry, it's because they have no clue what they're talking about. Okay? So lots of linkages that go into it. We see lots of polymers. We'll talk about polymers next week because I think this is a good time to bring it back in. And polymers do show up on the exam, okay, on the final exam. So we'll talk about polymers again. So it's recognizing patterns and kind of shortcuts within those and how those functional groups link with each other. Okay? For instance, if we ignore all of the stuff that's up there, because there's almost all the stuff that's up there, let's just focus in here. What do you see in there? Okay, I see a reference to a carboxylic acid. Yes. What else do you see? An amine. What do we know about our amines? They're what? No. They are basic. If they are basic, what else are they? They are decent nucleophiles. What do we know about our carboxylic acids? They're acids. There is an electrophilic site within that as well. Okay. We have the potential for our nitrogen to share electrons, form a tetrahedral intermediate, reform our carbonyl, and kick out OH. Forming what type of bond? Yeah, I heard it, but I'm trying to draw this all out. That purple bond is an amide bond. Or if you're a biochemist, it becomes a peptide bond. Stupid. Sometimes you just got to accept your losses. Okay? Why do they call it peptide? What are our proteins also known as? Polypeptides, meaning multiple peptide bonds. Why don't you just call it a polyamide? Because it's the same freaking thing. Okay? So, you will encounter lots of weird nomenclature changes, recognizing those changes both on standardized tests and in future classes, just realize. Okay? And even feel free to call me out in front of your biochemical teachers. Be like, well, my organic chemistry teacher called you an idiot. And they'll be like, that's because you are an idiot. He'll probably, or he or she will then probably say, no, I'm really an idiot. That's fine. I accept that. Okay? So within this section, the reason why they're bringing it up is that we're looking at our electrophilic carbonyls with the potential for leaving groups and the presence of some nucleophile. Okay? This is really, really important chemistry when we're looking at biochem because all of our proteins are made up of amide bonds. How do we make amide bonds? Well, we just went through an entire unit discussing amide bonds and really how they're formed, okay, or the chemistry behind them. So when we're looking within this section, they start talking about different ways that we can degrade proteins. Because that protein degradation is now a tricky thing to do, specifically, somebody's name gets attached to it. So it's not just that they're being a jerk and attaching their name. They legitimately came up with some tricky chemistry. Okay? They're using different reagents. All of those reagents involve nucleophilic addition and elimination and some weird other crazy stuff. Okay. How many people are excited to look at a detailed mechanism of this? How many people would like me to just kind of skip over this? No hands. Okay, I guess I gotta go slow. Okay, we could do a partial hydrolysis of protein. No, seriously, like, you guys don't want me to talk about it, right? I don't really want to talk about it. But it's there. So, where that takes us to